The James Webb Space Telescope has made a truly astonishing discovery: beams of light that appear to be radiating from what looks like an urban area, located millions of light years away. This incredible observation has reignited global interest in the age-old question, are we alone in the universe? Focusing on Proxima Centauri b, the closest known exoplanet to our solar system, the telescope detected a series of unusually bright, pulsing light bursts. These radiant signals have led some scientists to wonder, could these be artificial lights? Could we be seeing evidence of an alien civilization? For decades, the search for extraterrestrial life has fascinated both the scientific community and the public. But now, we may be on the brink of a historic moment. The James Webb Space Telescope has captured what many are calling the most compelling evidence yet: light patterns on a distant exoplanet that resemble SETI lights here on Earth. This discovery has sparked both scientific excitement and cautious speculation, offering new hope that intelligent life may exist elsewhere in the cosmos. These possible SETI-like illuminations were observed from a remarkable distance of 4 light years away. NASA engineers were astounded, wondering how long these signals might have been waiting in the dark undetected, until our instruments finally became advanced enough to find them. Astronomer David Kipping from Columbia University described Proxima Centauri b as exceptionally complex. Unlike most rocky planets that absorb sunlight and radiate it as heat, this planet behaves in a unique way, likely due to its close relationship with its star. Proxima Centauri, the James Webb Space Telescope, played a critical role in this detection. Its unmatched sensitivity to infrared light allowed scientists to pick up on the planet's unusual light emissions and study its atmospheric behavior in unprecedented detail. These observations are helping astronomers better understand Proxima Centauri b's environment and assess its potential to support life. One of Webb's most impressive features is its ability to detect extremely faint infrared signals, even those that other telescopes might miss. This makes it especially well suited to confirm whether the suspected SETI lights on Proxima Centauri b's night side are real. Artificial lighting, if present, would emit within a narrow frequency band different from the broad spectrum light of stars, and Webb is finely tuned to detect such signals. The interaction between Proxima Centauri b and its star plays a significant role in shaping the planet's climate and conditions. Like Earth, the planet experiences a cycle of day and night as it orbits its star. However, due to its orbital pattern and proximity to Proxima Centauri, the temperature difference between the planet's day and night sides is extreme. If the planet possesses an atmosphere, one side could be intensely hot while the other remains bitterly cold. These dramatic thermal fluctuations are a key focus for astronomers. By analyzing how heat is distributed across the planet, scientists can make educated guesses about the composition and structure of its atmosphere. Once again, the James Webb Space Telescope proves invaluable. Its ability to measure thermal emissions allows researchers to explore the planet's atmospheric properties with remarkable accuracy. Interestingly, the timing of Webb's orbit around Earth aligns closely with Proxima Centauri b's orbital cycle. Every 11 point to Earth days, giving scientists consistent windows to monitor the exoplanet's daylight and nighttime phases. If Proxima Centauri b does indeed have an atmosphere, the next step will be to analyze its chemical makeup. Detecting elements like oxygen, water vapor, or methane could indicate that the planet may be capable of supporting life. Such a discovery would mark one of the most significant milestones in human history. While the James Webb Space Telescope JWST is exceptionally well suited for studying planetary atmospheres, it isn't designed to handle every aspect of exoplanet research. It excels at detecting key compounds like water vapor, carbon dioxide, and methane, substances that are often linked to biological activity. However, it is less capable of identifying free oxygen, one of the most definitive indicators of life as we know it. That said, JWST can still detect other vital signs such as ozone, which may signal the presence of a stable, life-supporting atmosphere. As scientists continue analyzing the wealth of data gathered by JWST, the search for distant, potentially habitable worlds presses on, bringing us ever closer to answering the age-old question, are we alone in the universe? It's important to remember, however, that JWST can only study a limited number of nearby exoplanets. For more detailed investigations into atmospheric composition, astronomers will increasingly rely on ground-based observatories, like the extremely large telescope belt, set to begin operations in 2027. the ELT is expected to offer more precise observations of planetary atmospheres, greatly enhancing our understanding of their capacity to support life. Excitement continues to build around the launch of future telescopes like the ELT. In the meantime, JWST remains a vital tool, offering unprecedented glimpses into the atmospheres of faraway worlds even with its limitations. Its discoveries are already reshaping our view of the cosmos and what might exist beyond our solar system. To improve the detection of exoplanets, upcoming space telescopes will feature cutting-edge technologies designed to block out the intense glare from stars, similar to shading your eyes from the sun to see more clearly. These innovations will help astronomers observe the faint light reflected off distant planets. This is critical for analyzing their atmospheres and determining whether they might be capable of supporting life. Yet observing exoplanets is no simple task. Stars shine far brighter than the planets that orbit them, making it difficult to detect the faint planetary light. To address this challenge, scientists are developing advanced methods like the coronagraph, a device placed inside a telescope to block starlight, while allowing the much dimmer planetary light to pass through. By shaping light waves carefully, coronagraphs can drastically reduce the brightness of the star, revealing the hidden planets nearby. Another promising technology is the Starshade, a large, flower-shaped spacecraft that will fly thousands of kilometers in front of a space telescope. It blocks out starlight before it ever reaches the telescope, allowing only the planet's reflected light to be analyzed. Starshades are especially useful for observing planets within the habitable zones of their stars, regions where conditions might allow liquid water and possibly life. These technologies demand extreme precision. For example, a starshade must maintain alignment to within fractions of a millimeter over vast distances. On top of that, they must be engineered to operate reliably in the harsh, energy-limited environment of space. Despite these significant challenges, the scientific payoff could be immense. If successful, these innovations will open an entirely new chapter in space exploration, allowing us to study alien worlds in extraordinary detail, and perhaps even identify planets that host life. Studying and analyzing the atmospheres of exoplanets could lead to the detection of biosignatures, chemical indicators of life such as oxygen, methane, or water vapor present in specific ratios. These molecules, if found together under the right conditions, could suggest the presence of biological processes and potentially confirm that life exists beyond Earth. Researchers are also working on ways to directly image distant exoplanets in greater detail. Future telescopes may feature advanced adaptive optics, which correct for distortions caused by Earth's atmosphere or the telescope's own movement, resulting in much sharper images. When combined with starlight blocking technologies like coronagraphs or starshades, these innovations will not only enhance our ability to detect exoplanets, but also enable scientists to map their surfaces and study their climates with far greater precision. This kind of direct imaging would mark a major breakthrough in our ability to assess exoplanets and evaluate their potential to support life. The development of next-generation space telescopes is a critical step forward in the search for extraterrestrial life. As our capacity to observe distant worlds improves, so does the possibility of discovering life elsewhere in the universe. Of finding that could radically alter our understanding of our place in the cosmos. The future of space exploration and the quest to uncover alien life is progressing at an unprecedented pace. As astronomers continue to investigate the nature of far-off exoplanets, the James Webb Space Telescope is leading this new era of discovery. The data it collects is helping scientists unravel the mysteries of these distant worlds, their structure, composition, and potential habitability. With every new discovery, we move closer to answering one of the most profound questions in science: is there life beyond Earth? The identification of Proxima Centauri b is just the beginning. It could mark the start of a transformative chapter in humanity's exploration of life in the universe.